Hello and welcome back to Data Science CastNet. Today's video I wanted to showcase this paper that came out today and then also a couple of other related ones, all around this idea of using more compute at inference time in more innovative ways. Alright, so inference time scaling has been the buzzword recently, the big talk being reasoning models, right? So reasoning models like DeepSeek R1, incentivizing reasoning capability in LLMs via reinforcement learning. The highlight feature is that they spend more time, quote unquote, thinking before producing a final answer, and they do that by sequentially producing more and more tokens, right? So if you look at the DeepSeek R1 training, what happens over time as they learn this process is they're spending more and more tokens, quote unquote, reasoning over the question before they get to a final answer, right? So here's the average response length during their training. And it learns to solve these reasoning tasks with more thinking time. The response length goes up from a few hundred to possibly over 10,000. And we see this with other thinking models as well. This is why, for example, if you ask a question of O3 in ChatGPT, it's going to take a while before you start seeing your final answer output. Versus something like 4.0 or 4.1, which are models that just immediately start producing the output. Right, so this gives a very impressive improvement in performance, but at a cost of latency. It takes a really long time before your answer starts coming out, and so it's very computationally expensive to run these models. So a big question has been, is this the only way we can scale up inference time compute, or are there other options? So this paper today, they introduced something called parallel scaling. The idea is that we're going to be able to somehow do multiple forward passes through the model in parallel and then aggregate those results and get a better performance. And so they introduce this technique, and they say that they find that it works really well, and they have a so-called scaling law for how well it works. They say a model with p-parallel streams is similar to scaling the parameters by something on the order of log p, right? So you get the same performance as a larger model by doing some number of parallel streams instead of scaling the total number of parameters. And you can even apply this to an existing off-the-shelf model. You can convert it into one of these parallel models. And so, yeah, they kind of compare this with scaling up a model, just getting the model itself larger, right? More layers, wider layers. Takes a lot of time, specifically because loading all of those weights from disk into memory is slow, and then there's a lot of computation. And so inference time scaling is something like DeepSeek R1 or O1 from OpenAI. You have a model and it produces multiple tokens, and so this takes a long time. You're doing the same model for lots and lots of tokens before you get to the final answer you actually care about. So they're parallel scaling. Instead, they're going to take the input, they're going to transform it somehow, so you'll have multiple different versions, and we'll talk about how they do that. Those will all flow through the model in parallel, and then we'll aggregate those into a final prediction just for the next token. And they find that using this parallel scheme versus just a single prediction as normal gets you lower loss as you scale up the model. This trend holds, so you can kind of get the equivalent performance of say a 4 billion parameter model with maybe only 2 billion parameters plus 8 parallel streams. And this gives you lower memory, right? Because you only have one copy of the weights, and then you just put say 8 versions of your input through, especially at batch size 1. As the batch size increases, you're spending more time doing the computations and less time worrying about loading from memory. So a lot of their gains are going to show up at especially low batches. But especially cases where, you have single batch inference, you care about latency. They're showing that you can get much less latency and memory needed to get the same performance using their new technique. So very, very exciting if it holds up. Very cool potential paper. Okay, so a few questions you might have. How do we do this? Like, what do we change from a normal transformer model to be able to do this kind of parallel scaling? And then are there any other options for using the same set of weights mostly to do more computation for every next token rather than producing lots of reasoning tokens? And that's where the other paper we'll look at today comes from. Okay, so they go through introduction, explaining the background, introducing their idea that this parallel scaling is going to be powerful and have some sort of scaling law. And they compare it to some other options. Inference time scaling, producing lots of tokens, it's very slow. MOE scaling, you can do this very quickly, but it does require a lot of memory, and also kind of tricky to train sometimes. Dense scaling, just scaling up the model. So they say their approach is going to be great. Some of the background and motivation is fun. So they reference classifier-free guidance, one of my favorite techniques from the diffusion world, and then adapted into NLP as well. The idea is that you would take an input, right, like a noisy image that you want to denoise, and instead of just doing a single prediction, you would do two, one with some conditioning information and one without, is the typical way it's done. And so the intuition historically has been that, look, the model's going to be, predicting some sort of mean, and you want to sharpen it and push it away or push it further in the direction of the conditioning. There's all these hand-wavy things about the model doesn't pay too much attention to the conditioning, so we're forcing it to pay more attention. This is another way of framing it, which is to say, look, if nothing else, this is also letting us do twice as much computation, right? And so whatever else it's doing, it's also just letting us spend 2x the compute on the single input to make a single prediction. Maybe that's part of why it does better somehow. And so, they say, why can't we just learn the capability of this CFG? Now, there's ideas of distilling classifier-free guidance into a single step. Maybe that's not such a question, but the idea of having more computation seems like that could be useful, and they kind of use this as their story for how they came to this idea. Okay, so we'll look at exactly how they implement this parallel computation, and then we'll look at the results, and we'll start with the results. I think that's the way they frame it here. Can we get the same effect as scaling up the model just by using this parallel scaling? Sure enough, they find they can. So they train on the stack, which is mostly code data, training from scratch. They also train on the pile, which is mostly just general, I think, web text as well. And they find these kind of training curves. As we increase the number of parameters, the loss goes down. As we increase the number of parallel streams, the loss also goes down, right? And so you can kind of compare and say, for a given loss value, a 1.6 billion parameter model might be almost as good as a 4.4 billion parameter model in the case of the stack. And they note that the that sort of ratio, right, the amount of benefit you get from these parallel streams, this k value here, is different for these two data sets. And so they kind of flag this idea that, hey, maybe the stack, which is a lot of code data, requires more reasoning, whereas the pile with a lot of web data requires more memorization. And so scaling parameters is going to help more with memorization, but scaling compute, like just the raw amount of compute that you do, is going to help more with the code side of things. And so that's one like big thing that they pull out of their results, is to say, hey, maybe this is like, it's good in general, and it's especially good for reasoning, this parallel scaling. Okay, so here's another way of viewing that same thing. For a given loss value, you can either scale parameters or you can scale compute, and they fit some sort of scaling laws to this. They find that you get a significant boost in score by scaling up either of these things, right? And so you can kind of, again, compare a larger model, but no parallel scaling versus maybe a much smaller model with 8 streams in parallel going through. And they say model parameters mainly impact the memorization, while computation mainly impacts reasoning skills. A very bold claim, but it seems like it's definitely supported in some of their experiments. Okay, and then they also evaluate on downstream tasks, like I think this is human eval, mostly basic Python programming. So for these really small models, these are darn impressive scores. I think later we'll see some comparisons. So yeah, a few things worth mentioning. The models, they keep the same number of layers, so when they talk about scaling up, they're just making the layers wider rather than adding more layers. So there's some nuance there. As I said, these methods are very effective because you load the weights once, then you're feeding effectively a batch of 8 samples through, rather than loading a model 4 times as big or 8 times as big and putting a single batch through. So you get a lot of efficiency gains. Then let's see, they do some scale up. Okay, so here's an example training on 1 trillion parameters. The baseline is trained the same way as the different parallel versions. So there's no like, oh, we trained a purposefully bad baseline. It's just parallel scale equals 1 is kind of like, what if we trained a vanilla transformer? And so you can compare these numbers to see, yes, we do get an improvement across all of these downstream tasks. And then if you want, you can compare to some of the existing small models and see that they're rivaling some models that are larger and trained on much more data. And so, very impressive results. I think the final thing they do is they also train normal fine-tuning for a very long time, and then right at the end switch to this parallel stream training, and you can see even starting from this model that's already been trained just like a normal transformer, switching to their parscale version, you still see an improvement for the parallel 8 case. And so this motivates like, hey, what if we just took an off-the-shelf model and continued to train it a little bit with this pass-scale setup, much fewer weights, and you can see again, so starting from a fairly low loss, this is Quen 3B, I believe, Quen 2.53B. Yeah, again, they are able to see an improvement in performance on downstream tasks, even if they're just training the few extra parameters that they use for the parallel scaling. Okay, so I think we should talk now quickly about how they do this, and then look at some different alternative approaches as well that I think are worth considering and that might be like synergistic with this. And so they've put the actual implementations down in an appendix. Okay, so one part is I have 8 different versions of my input, and we'll talk about the way they get the different inputs. I feed them through my model, right? So I have just parallel pass through. It's one backbone. There's no like multiple copies of the model. How do I aggregate those 8 outputs then into a final prediction for the output hidden state, or for the like what's the next token actually going to be? And so they concatenate the outputs together, and then they use an MLP to go from like 8 times p, where p here is probably the vector that you're trying to aggregate, shrink that down, and so yeah, they're just finding a scaling and then weighting those different parallel streams, I guess. And then, okay, so you can imagine if we were randomly initializing things so that we're going to have different variants flowing through, if one of those happened to be particularly bad, it might not be useful for the final task, especially at the beginning of training. And so any weighting scheme might learn to ignore that early on. Similarly to how with a mixture of experts models, you have this kind of imbalance where you end up with quote-unquote lucky experts that get most of the weight. And so taking strategies from those types of problem, they have this label smoothing that just makes sure that each stream gets at least some participation, and so over time they're still able to learn to be more useful, and you don't end up with only 3 of the 8 parallel streams getting trained at all. So that's their aggregation at the end. The other half is how do we change our inputs, right? And so they tried variants where you just use the same inputs, but you applied a different LoRa to the model for each of the 8 inputs. They also tried bitfit, which I think they don't really go into the details much. Maybe another parameter efficient fine-tuning method. Or you could just add a different prefix. And so that's the simplest method. That's what they settle on. So if we go back to the picture right at the beginning, I have my input sequence here. They have a learned 48 token prefix for each of the different parallel streams that just gets prepended ahead of the input before it goes through the model. So you can keep the model weights completely frozen. You just create 8 different versions of the input by stacking different sets of 48 learned, embeddings at the start of each sequence. And then this learnable aggregation here is their, MLP softmax weighting aggregation that takes those 8 different set of outputs and combines them into one that you can use to predict the next token. So very cool paper, very impressive results. I'm very excited to see if this holds up and see what people do with it. It's particularly exciting to think that you could take any existing model, right, even some pretty large existing models, fine-tune it for a relatively small amount of time, right? So they talk about, they train for 1 trillion tokens and then they train for 20 billion tokens to add this parallel stream capability. And potentially that could even mean just learning the prefixes and the aggregation, right? I think they do an experiment here with, here, this is the model is frozen, so we're just learning those 8 prefixes and the aggregation function, and they see a significant improvement on some downstream tasks, and specifically coding, I believe, with very few parameters being trained for a very short amount of time compared to the base training. So yeah, potentially you could take any off-the-shelf model, convert it into one of these parallel scaling models, and especially for local inference, have a much better model with much lower latency and fewer parameters than the equivalent scaled up model you would need to get that same performance. Okay, so fantastic paper, very cool. And then just as a little addendum, I wanted to show I think less well-known paper potentially from some folks at Sakana AI that I met at ICLR, which is why it's fresh in my head. Yeah, very cool paper, also tackling this idea. How do we spend more compute when predicting a single next token without adding more parameters. And so they're going to also start from an existing model, and they're going to try and adapt it so that they can do multiple different forward passes before getting their final answer. But rather than doing it in parallel like this, they're going to do it sequentially, inspired by diffusion. And so I'm not going to go deeply into this paper. I might do that in a future video. Highly recommend, diving in if you're excited. But the core intuition here is to say, like, we can treat the prediction of the next token as predicting a distribution of likelihoods over the different possible next tokens. And so what if we fed in some noise and tried to predict that distribution? But then instead of just sampling from that and going like we do in a normal language model, that's what a normal language model prediction step almost looks like. What if instead we only moved a small direction from noise towards that predicted distribution, and then we fed that back through again and again and again? And so obviously the model's not used to taking in a noise vector and predicting the next token, right? It's used to taking in the previous token and predicting the next token. So they do have to change the model, and they do that in a very parameter efficient way by just applying LoRa. So you have your, sorry, not just LoRa, but applying like a separate path through the model. So you can see here LM parameters, this is the original model parameters, L2D parameters, and these are initialized from the original model, and they're just those original weights adapted with a LoRa. So it's very few actual extra parameters, even though it looks like it's a whole separate parallel stream. And so normal language model takes in the embeddings for some token k-1 and produces the logits for the token k. In this case, instead, they're going to take in some embeddings, but they're also going to take in some random sample of a time step, right, for how noisy this is going to be, and then we're going to try and do effectively diffusion on this noisy representation as it passes through here, using cross attention to the keys and values from the language model forward pass, so you can save on computation that way. Anyway, so I don't want to get too much into the weeds of the specific implementation, but the core idea here is that during inference we are going to, rather than just feeding a sequence through a single time, we're going to take a sequence, and then we're also going to take some noise, and for some number of time steps we're going to sample y, like the prediction for the next token, but we're going to update our noisy sample that we're quote-unquote denoising, like we're diffusing on, just a small bit at a time. And you'll see this kind of like flow matching variant that they do, and they leverage the fact that the predicting from the most noised version to the final denoised version is effectively what the model has already been trained to do, and they experiment with different samplers and so on. But the core finding here, the core finding that I want to highlight, is that this framing of being able to like sequentially apply the model again and again to predict just the single next token, it gives you this improvement in performance with more forward passes, right? So with a single forward pass, we have average score on some benchmarks of 28. With 3 forward passes, we have an average score of 32. With 7 forward passes, we have an average score of 35. And so like diminishing returns as you scale up, but some definite returns as you scale up. And importantly, this is not like going through 3 times the depth of completely separate parameters. It's the same parameters reused, just with different time steps and on slightly different subtle versions of the input. So you can see the kind of correspondence here between these two. Now the downside of this is we're having to do, say 8 forward passes in sequence, right? So you're not getting some of the latency or efficiency gains from being able to do that in parallel. But it does tell us that maybe this is yet another axis along which we could scale. And all 3 of these can combine, right? So you can imagine a reasoning model that produces lots of reasoning tokens before the final token. But for each of those reasoning tokens, it's doing multiple parallel forward passes, right, with some augmentation or differentiation. And then it's getting a higher quality prediction. And then maybe it's not even using that prediction immediately, but it's feeding that prediction through again and again in this kind of like diffusion-y way. And so these all give us different axes along which we can scale. The Quen paper and everyone who's thinking about this is obviously like hinting at like this is spending a lot of compute for every token. We can definitely do better than that by learning perhaps if the speculative decoding model or the first pass through the model is already highly confident, maybe we don't have to do the second and third and fourth and fifth steps, right? I think the large language model diffusion paper, they experimented with like some kind of early stopping or dynamic allocation of how many steps to do depending on how difficult it is. This parallel scaling one here as well hints that like, oh, there's you can have a frozen base model, right? That experiment where they trained just the 8 different parallel versions and the aggregation head. Say, look, if we want, we could keep the same frozen base model and we could choose to do 1 in parallel or 8 in parallel, depending on how difficult the token looks like it might be to predict. And then, yeah, like with the reasoning, by producing many tokens aspect, again, if it looks like a simple problem, you could potentially try and incentivize it somehow. Like, for example, the Kimi paper, Kimi, that I need to add to my Zotero library. They added a length penalty basically to try and teach the model to know when it should spend lots of tokens and when it shouldn't. If it's an easy question, it shouldn't spend lots of thinking tokens. So between all of these things, these are all ways of differently scaling how much compute we allocate at inference time. These by adding more tokens, and these two by adding more compute per token. And I think it's really promising to see these different options appearing, and hopefully this video encourages people who are experimenting with this to maybe try combining some of those or exploring them, maybe try implement this parallel scaling yourself for your favorite model of choice. It seems like a really interesting and exciting area. Cool, thank you for watching. That's all I have today.